All right, so here are the vital stats here, right here. Vital stats for our friend Mercury. So named after the god of, the messenger of the gods, like the little flower dude with the wings on his feet, because Mercury orbits the sun so quickly. Okay, so named Mercury. Not all these numbers are particularly interesting. Some of them are. In fact, there's actually a story behind all of them, but we're going to pick out one story in a moment and tell it. But what I want to do first is just quickly go through these numbers here quickly. Semi-major axis. These are in order of your planet table that you've got. It says planets across the top. Semi-major axis is 0.38 AU. All right, so spins most. It's on average. It is. Its distance to between the sun and Mercury is about 38% that of the Earth. Takes about 1/4 of an Earth year to go around once. 0.24 Earth years. Requires 59 days to rotate once. It's a slow rotation, right? Our Earth rotates once a day. Our Earth rotates 59 times for every one time Mercury rotates. So it's a very slow rotation. It's not very much mass, 0.055 Earth masses. The radius is 0.38 Earth radii. So it's about 40% the diameter of the Earth. So it's bigger than the moon. Okay, it's bigger than the moon, but not by a whole lot. It's got no moons. Numbers of moons is 0. The density is just slightly less than that of Earth, so it's rocky. As we'll see, the rocky planets, the inner planets, Mercury, Venus, Earth, and Mars are all going to have pretty big numbers here. And then when we get out to the gas planets, that number is going to drop because we're talking about gas and not solids at that point. Mercury, very interesting. There's a physical reason for this. The Earth is tilted 23.5 degrees. That's our obliquity. But Mercury is almost perfectly. It's actually it's like 0.03 or something like that degrees. It's very slightly tilted relative to the ecliptic, but not much. What's the units on this? Magnetic field, 0.05 times the field of the Earth. So it's got a field, magnetic field, but not nearly as strong as Earth's. It has a highly eccentric orbit, the most of all planets. Now, back when Pluto was a planet, Pluto's eccentricity is slightly higher, but 0.21 means there's a 20% difference between the closest approach of Mercury and the Sun and the most distant approach. So the closest distance between Mercury and the Sun is 20% closer than the furthest distance. So that's quite a big change. It's like changing between 80 feet and 100 feet away from something. Okay, so it's, significant amount of difference. And the surface temperatures, I've got the Fahrenheit listed first, but on your table I've got Kelvin. Kelvin is a temperature scale used by scientists. The zero of the Kelvin scale is called absolute zero, and no physical object can reach absolute zero. It's a lower limit on temperature. So the Kelvin scale has a reading, there's no negative Kelvin temperatures. It's all positive. So 89 is actually quite cold in the Kelvin scale. It's equal to negative 300 Fahrenheit. So the coldest it gets on Mercury is negative 300 Fahrenheit. The hottest it gets is 225 degrees Fahrenheit. Okay, so very hot. So the range of temperatures on Mercury is enormous. And that's because it's so close to the sun, it spends and one face of the sun stays pointed toward the sun a long time, and it gets quite hot, and then when it rotates away from the sun, it gets quite cool. There's no atmosphere to moderate those temperatures. So the temperature swings on Mercury are enormous, and the same as they are on the moon. Notice that Chapter 8 is about the moon and Mercury. They oftentimes are thought of together because there's a lot of similarities. And one of them is the fact that their temperature swings are both so enormous. Okay, so those are the vital stats for our new friend Mercury. But what I want to point out here, what I want to dig into a little bit, these two numbers right here. Let's do a little math with those. Let's actually look at those two numbers a little more closely and put them in the same units, okay? If we do that, we'll find that the 0.24 Earth years, the orbital period, piece of orbital period, same as P sub O, is equal to, if you look a little more closely, it's 87.97 days. So that's how long it takes Mercury to orbit the Sun, which is equal to 0.24 Earth years. 87.97 days is the same as that number, just converted into days. That's about a fourth of a year, right? So that's the orbital period, and if you compare that to the rotational period, so this is, another way of writing this is PO and this is PR, same thing. Okay, I just wrote them on the blue list to match what you've got on your planet table. PR, if you do that, you find that it is 58.65 days. So, those are our two numbers. It takes Mercury 87.97 days to orbit the Sun. It takes Mercury 58.65 days to rotate once upon its axis. All right. Now, if you see those two numbers, okay, and you start messing with them, you realize there's something going on with those two numbers. That they're very simply related to each other. If you take 87.97 and divide it by 58.65, you will get almost exactly 1.5000. Now, if we keep going, you'll see that it does change a little bit, but that's just because my numbers here are not perfect. But the point is that there's a ratio here of 3 to 2. Okay? There's a ratio here of 3 to 2. And we'll see what that means, okay? These two numbers are simply related to each other. That's what I'm trying to say. What we're seeing here is similar to what we saw with the moon. Remember, the moon had a 1-to-1 spin-orbit resonance. It rotated once for every orbit. Mercury has a 3-to-2 spin orbit resonance. Okay? It's 3-to-2 spin orbit resonance. And then we're going to see exactly what that means in the very next lecture. I mean video.